Video on exponential growth and decay. So this is the introduction to the video, and I'm just going to give some examples of what exponential growth and decay are, and then we're going to look at what it means in maths and what you need to know for GCSE maths. So the graph on the left shows world's population growth over the past 2,000 years. So as you can see, there's a J curve. And what this means is that population has grown exponentially. So if you've studied population in geography, you will have heard this term, that population has grown exponentially. And what that means is that over time, population has got very big, very quick. So as you can see, the graph accelerates, it gets very big and very steep very quick. So that's an example of exponential growth. And then exponential decay, we can see that the graph goes the other way. So it sort of dips, if you like. And this is to do with half-lives and radioactive decay. So in physics, if you've studied radioactivity, you will know about half-lives and how radioactive substances break down and decay. So they're examples of exponential growth and decay. But what does it mean in maths? So in our straight line equations, we've seen the equation y equals mx plus c. And that's just the general equation that all straight lines look like. So is there something like that for the exponential? And there is. It is y is equal to k to the power of x. So that is what all exponentials look like, where k is just a number. And we can sketch this. So an exponential graph of exponential growth. So if this is y and this is x, the graph may look like something like this. So just like with the population growth, we have this J curve. And the graph has some very important properties. They are that it crosses the y-axis at 1. So it intercepts the y-axis at 1. So it has the coordinates 0, 1. And also, the graph is asymptotic with the x-axis. So it means that it never touches or never intercepts the x-axis. So going back to the point where it crosses the y-axis, so the y-intercept at the point 0, 1. Well, how do we know that it's 0, 1? Well, we can prove it. So we take our equation, y is equal to k to the power of x, and we substitute x is equal to 0 in. So x is equal to 0, so that will leave us with k to the power of 0. Anything to the power of 0 is 1. So k to the power of 0 is just 1. So we're left with y equals 1, which is what should happen, that we should get this. So, as I've said, these are some very important points about the exponential curves that we see in maths. And we're going to look at some more sketching in the next part of the video, and then some exam questions later on. So in the next part of this video, I want to look at sketching and drawing an exponential. So if we have the equation y is equal to 2 to the power of x, so we know that this is going to represent an exponential graph because the exponentials are of the form y is equal to k to the power of x. And that was in the first part of the video. So that's the general form, y is equal to k to the power of x. So k is just any number, and in this case the number is 2. So if we want to draw this graph, we set up our xy table as we would usually. So we'll start at -3, have -2, -1, 0, 1, 2 and 3, and then we'll work out the values for y. So substituting x in, so we got 2 to the power of minus 3, and that's 1 over 2 cubed, which is an eighth. Then minus 2, so 2 to the power of minus 2, well, that'll be 1 over 2 squared, which is a quarter. And then 2 to the power of minus 1, well, that'll be 1 over 2 to the power of 1, which is a half. Then we've got 0, so when x is 0, 2 to the power of 0, well, anything to the power of 0 is 1. Then 1, which will give us 2. Substituting 2 in, 2 squared is 4. And then 3, which is 2 times 2 times 2, which is 8. So they're the y values. Then we would just set up our axes. So we've got y. So we'll go up. And then we've got x. So we'll have 1, 2, 3. Just keep going with those. 1, 2, 3, 4, 5. This way we'll have 1, 2, 3, 4, 5. So these are the negatives. Minus 4, minus 3, minus 2 and minus 1. So you may notice that I haven't drawn any negative y numbers. Why is that? Well, we know that the curve is asymptotic, so it will never cross or touch this x-axis, so we don't need them. That's absolutely fine. And then the positive y value, so we'll go up in 2s here. So 2, 4, 6, 8, 10. So I'm just going to zoom in slightly. So then we just plot the points. So minus 3 was an eighth, so that would be somewhere very down here. Then minus 2 was a quarter, so that would be slightly higher. Minus 1 was a half, so again slightly higher. I'll put these numbers on actually, so 2, 4, 6, 8, 10. And then we went on to 0. So 0, which is 1 on the y-axis. And we know that it must cross that point because, as discussed at the first part of the video, the exponentials have that property. So when we put 0, we get y is equal to 1. So it must cross this y-axis at that point, at the coordinate 0, 1. And then 1 will give us 2. 2 brings out 4. And 3 gives us 8. Okay, and then we do a sketch of our curve. So it shouldn't touch the x-axis. And then we come up like so. Keep going. As you can see, we've got that J curve. It crosses the point 1, 0, and it doesn't touch the x-axis. So if you were asked to do this in exam, those would be the things that they would be looking for, the examiners would be looking for. So now we're going to look at a few exam style questions. Okay, so this is an exam style question, which is related to the exponential growth and decay topic. So it says here is a sketch of part of graph y equals p q to the x, where q is greater than 0. So they haven't given us the negative part, we've just got the positive part of the 4 quadrants. It says the points 0, 5, 2k, and 4, 405 are all on the graph of y equals pqx, obviously on this graph, so these points. and then find the value of k. So we've got points, we have an equation, and we need to find k. So what we'll do is we'll start substituting some of these points in and see what we can do. So firstly, we'll start with the coordinate point 0, 5. So 0, 5. This is just a colon. So the left hand coordinate is x, the right hand is y, and this was all into the equation here. So we'll have that 5, because that was y, is equal to p q to the 0, and that means that 5 is equal to p times 1, so p times 1, because anything to the power of 0 is 1, so that just means that 5 is equal to p. Okay, so now we've got something that we can maybe work with, so we'll keep going, and we'll leave the 2k part, because we don't know what k is, that's what we're trying to work out, so we'll go to 405, so this coordinate point, so again, left hand coordinate is x, the right hand is y, so we'll do 405, because that was y, and that is equal to p q to the power of 4 . Now, we've already worked out that p is equal to 5. So from this, we know that p is equal to 5. So we can substitute p into this, which will help us. So we've got 405, which is equal to 5 q to the 4. And then we can solve this for q. So we'd do 405 divided by 5, and that leaves us with q to the 4. So 405 divided by 5 is 81, and that's equal to q to the 4. So then we go onto our calculator, we press shift and then the button to put in any power, and that will let us do this, where we can get rid of that power. So it's the quartic root of 81, and that's 3. Okay, so what have we worked out so far? Well, we've worked out a value for p, and we've worked out a value for q. And then the question was asking us to find the value of k. So we can go back now, we can substitute, well, for y is equal to p q of x. So we can substitute this coordinate part in, so k is equal to p q squared. We know what p and q are, so q is 3 and p is 5, so we'll substitute those in. and that's equal to P, which was 5, and that's multiplied by Q squared. Q was 3, so we've got to square that, and then we'll just work that out. So 5 times 3 squared, to put that into the calculator, well, we know that 3 squared is 9, so it's 9 times 5, which is 45. So the value of K is 45. So therefore we could just put, therefore, K is equal to 45. This is another exam style question on the exponential growth and decay topic. So it says that Louis and Robert are investigating the growth in the population of a type of bacteria. They have 2 flasks, A and B. At the start of day 1, there are 1,000 bacteria in flask A. The population of bacteria grows exponentially at the rate of 50% per day. So it says, show that the population of bacteria in flask A at the start of each day forms a geometric progression. Okay, so the first thing to note here is that the bacteria is growing at a rate of 50% per day. So there's a percentage increase of 50% per day. So when we have percentage increase questions, usually, so if it was a 3% increase, we write that as 1.03. That's what we would multiply by. So we've got 50%, so we will be multiplying by 1.5. Okay, so then the question says that at the start of day 1 there are 1,000 bacteria, so the first term will be 1,000. Then we take 1,000 and we times it by 1.5, and that will give us the second day, which is 1,500. And then we take that and we multiply it by 1.5, and that will give us the third day, which is 2,250. And again, we take the 2,250, times that by 1.5, and that will give us the fourth day, which is 3,375. So then, this is obviously a progression. And how do we know that it's a geometric progression? Because every time each number goes up by a factor of 1.5. 1.5, and obviously it will keep going, so we'll put dot, dot, dot. So then all we need to do to state that it's a geometric progression is put that there is a common ratio. So common ratio of 1.5. Part B of the question says the population of bacteria in flask A at the start of the 10th day is K times the population of bacteria in flask A at the start of the 6th day. Find the value of K. Okay, so I'm just going to come back to part A, and every time we multiply by 1.5, and we started at 1,000. So is there a faster way that we could work out what a term of this progression would be? And there is. So if we wanted the third term, we could say, well, we've got 1,000. We can multiply that by 1.5. If we want the third term, we'll just square 1.5. So we get 1,000 times 1.5 squared. And that is equal to 2 0.250. So it's a little bit like compound interest. Well, in fact, it's a lot like compound interest. And that's where we're really using the formula for compound interest in this question. So if we wanted the third term, we needed to raise it to the power of 2. So if we're after the 10th day, that means we're going to need the 9th power. And if we want the 6th day, we're going to need the 5th power. So it says that the population at the start of the 10th day is K times the population of bacteria in the flask at the start of the 6th day. So the 10th day, so we'll do 1,000 times 1.5, and it was the 10th day, so we want the 9th power, and that's equal to K times the population at the start of the 6th day. So it would be K times 1,000, because it was K times the population, and then it was the 6th day, so we want the 5th power, so times 1.5 to the 5. And then all we need to do is rearrange this for K. So we get that K is equal to 1,000 times 1.5 to the power of 9. That is a 9 divided by 1,000 times 1.5 to the power of 5. We just type that into our calculator and work that out. So we get 1,000 times 1.5 to the 9. And it's that answer divided by 1,000 times 1.5 to the 5. And our answer just comes out at 5.0625. Doesn't say about rounding, so we'll just leave the answer as it was on our calculator.